we are discussing non-linear fiber optics. In last two lectures, we saw that when the light propagates inside the optical fiber, because of the intensity, the refractive index of the material changes, and because of that the pulse propagation gets modified. So, we showed that in general the induced polarization inside any material has a component which is this first order susceptibility. We also have a component due to second order susceptibility and third order susceptibility and so on. The first order susceptibility gives what is called the dielectric constant, and these are the nonlinear terms which we get in the dielectric constant. We also saw that for the material glass, the second order susceptibility is negligibly small, and therefore, we see the effect of the third order susceptibility, which gives the nonlinear contribution to the dielectric constant. And we took the case what is called the Kerr nonlinearity, where the refractive index of the material is related to the electric field square, that is the power density. So, you are having the refractive index of the material, which is the linear index, plus you are having this term which is coming because of this nonlinearity, which we call as the Kerr nonlinearity. And then starting with the wave equation, we derived what is called the nonlinear Schrodinger equation, which gives the evolution of a pulse on an optical fiber. We also saw that on an optical fiber, the nonlinear effect is enhanced by almost a factor of billion compared to the nonlinear effect in a bulk material. And that was for the simple reason that once the power is confined to the core of the optical fiber, then this interaction, the nonlinear interaction, keeps taking place over the effective length inside the optical fiber, which due to very low loss on the fiber, this length turns out to be a few kilometers. And therefore, the overall effect of nonlinearity observed inside the optical fiber is much stronger compared to what you see inside a bulk material. So, we saw that the power levels which normally we deal in the optical communication, even for those power levels which are a few milliwatts of power, the nonlinear effects become significant in the optical fibers. So, with that in mind, then we wanted to understand when the signal travels on the optical fiber, what way it will get modified. And therefore, we derived this equation, what is called the nonlinear Schrodinger equation, after certain approximation and certain linearization. And we saw that if you consider a pulse with an envelope function, which is given by this A, then it evolves along the optical fiber by this equation. So, here this term which is due to the dispersion on the optical fiber, this term is due to loss on the optical fiber, and this is the term which is due to the nonlinearity on the optical fiber. And then we saw that we can consider different cases depending upon what is the pulse width, how high the power is in the pulse. So, the different effects may dominate at different situations, and therefore, we define these three lengths or two lengths on the optical fiber. One we call as the dispersion length, other one we call as the nonlinearity length. And then we saw that depending upon the physical length of the optical fiber, sometimes the nonlinearity length may be smaller than the physical length, so nonlinear effects would dominate. Sometimes the dispersion length would be less than the physical length of the optical fiber, so the dispersion effects would dominate. And when both the lengths are smaller than the effective length of the optical fiber, then the both effects would start contributing, and that would give the evolution of the pulse. So, we saw that in three different situations, when L is much less than LD and L is much less than NL, the fiber becomes a bare medium of power transportation. The pulse does not get any evolution as it propagates in the fiber. If you are having L which is much greater than LD and L is much less than NLL, then the dispersion effects dominate, and we have seen already dispersion effect inside the optical fiber that gives you what is called the pulse broadening. Of course, we are going to see in a little more detail the analysis of this today. The third case was that the dispersion effects are not dominant, but the nonlinearity effects are dominant, and that will happen if you are having a large power inside the optical pulse. Then we get a phenomena what is called self phase modulation, that also we will investigate, and then when both the effects are present, then we get a pulse what is called a soliton. So, just to give you the few numbers, let us put some numbers and see under what situation what effects would start showing its presence. So, let us take a typical case of propagation. So, let us say we consider the wavelength of propagation, which is 50 nanometer, that is the optical window which is used. The beta 2 at that wavelength for a typical fiber is minus 20 picosecond square per kilometer. The gamma typically you see for the optical fiber is of the order of about 2 watt minus 1 divided by per kilometer. If you consider a data rate of 10 Gbps, and consider the power which you are transmitting P 0, let us say about the order of about 3 dBm. So, that is equal to 2 milliwatts. The data rate this would give the T 0, which is the pulse width, which is 100 picoseconds. So, P 0, which is the power in the pulse, that is 2 into 10 to the power minus 3 watts. So, if you calculate the dispersion length and nonlinearity length, that we will get as LD, that is equal to T 0 square, which is 100 picosecond square divided by mod beta 2, so which is 20. So, that gives the dispersion length of the order of about 500 kilometers. Similarly, we can calculate the nonlinearity length for this power. The gamma is given, which is 2 watt inverse per kilometer, and P 0 is 2 milliwatts. So, we can calculate from here 1 upon gamma P naught, that is equal to 1 upon 2 into 2 10 to the power minus 3. So, that is of the order of about 250 kilometers. So, if you consider a typical optical communication link, let us say the L is of the order of about 100 kilometers, then for this one you see that L is much less than LD, it is much less than nonlinearity length also, and therefore, in this situation neither we will see the dispersion effect nor the nonlinearity effect on the pulse propagation. Of course, note here that when we are talking about the pulse propagation, we are consider that the pulses are Fourier transform limited. So, here we are assuming that the carrier is the monochromatic carrier and the spectral width is coming just because of the modulation, which is this modulation. So, we are intrinsically assuming that we have Fourier transform limited spectrum. However, if we narrow the pulse width further, then for the same 100 kilometer link, we will start seeing the effect of the dispersion. So, for example, if you consider 40 Gbps data, that will give the pulse width T 0, which is 25 picosecond, and that will lead to the dispersion length, which is 625 T 0 square divided by beta 2, which is 20. So, of the order of about 30 kilometers. So, in this case, then we will see that the L is much greater than L D, but L will still remain less than L N L. So, for 40 Gbps pulses, if you transmit on the optical fiber, you will see that the dispersion effect will start showing up, because that is the situation which will prevail. But if we increase the power of the pulse from 2 milliwatts to let us say 20 milliwatts. So, if I make P naught, let us say about 20 milliwatt, then the nonlinearity length will reduce from 250 kilometers to 25 kilometers. Then if you are having a link length of 100 kilometers, you will see that the nonlinearity length also will become much smaller compared to the physical length of the fiber, and in this situation then the dispersion and nonlinearity both will start playing role in the pulse propagation. So, these are the typical numbers which normally we see inside the optical communication. So, what we find is that for the typical power levels and for the typical data rate which we are going to handle in the modern optical communication systems, the dispersion and nonlinearity both effects can become visible. So, now we are going to take the one by one the case and then see in little more detail what is the meaning of dispersion, what internally happens to the pulse when the pulse propagates in the presence of dispersion, what happens in the presence of nonlinearity, right, and when both are present, what would really happen. So, today we are going to take one effect and try to see how the nonlinear Schrodinger equation can be simplified in that situation, and then what way the pulse evolution would take place. So, today we are going to discuss what is the group velocity dispersion. That means, in the nonlinear Schrodinger equation, we are considering the term which is coming only because of the dispersion. So, today we are going to talk about group velocity dispersion. In short, we call it GVD. Now, for solving the nonlinear Schrodinger equation, let us redefine certain parameters to take into account the losses on the optical fiber. So, let us define a normalized amplitude u, which is a function of z distance and a time t, and we have defined this normalized time t. If you recall, this is the time in the moving frame with the pulse. So, the envelope function which we have in nonlinear Schrodinger equation, this is related to this u as square root of P naught, which is the power in the pulse, e to the power minus alpha z by 2, where alpha is the attenuation constant on the optical fiber, u z of t. So, from here we can get d a by d z, that is what we require in the nonlinear Schrodinger equation. So, that is equal to square root of P naught minus alpha by 2 e to the power minus alpha z by 2 u plus e to the power minus alpha z by 2 du by dz. So, if I take this dA by dz and substitute into the nonlinear Schrodinger equation, then we get the nonlinear Schrodinger equation as du by dz minus j beta 2 by 2 d2 u by dt square is equal to minus j e to the power minus alpha z divided by L n L mod u square times u. So, what we have done is we have taken the nonlinear Schrodinger equation as we have derived earlier, substitute into this equation for A in terms of u, and then we will get this equation. And now, you see the significance of why we define this quantity u in normalized terms, that after we define this, the term which used to come because of this loss, this term is now vanished. So, in this equation in terms of this normalized parameter, you have one term which is coming because of dispersion and one term which is coming because of nonlinearity. And the nonlinear length we already defined, which is 1 upon gamma into p naughts. So, this quantity is nothing but 1 upon gamma p naught. Now, assuming that the power level inside the pulses is not very large, that means this term is negligible, only the dispersion effects are present. So, since we are investigating here the group velocity dispersion, we are assuming that we have chosen the pulse parameter in such a way that the nonlinear effects are negligible. In this situation, this term essentially can be neglected, and then we have the nonlinear Schrodinger equation, which is du by dz is equal to j beta 2 by 2 d2 u by dt square. Now, since you are having a second derivative with respect to time, this differential equation can be solved if you take the Fourier transform of this equation in time. So, the equation can convert it into frequency domain. So, the second derivative will become simply multiplication of the square of the frequency, and this then equation can be solved very easily in the Fourier domain. So, if we define the Fourier transform u tilde of z omega, which is to infinity u z t e to the power minus j omega t dt, and the inverse Fourier transform as u z t 1 upon 2 pi integral minus infinity to infinity u tilde z omega e to the power j omega t d omega. So, I can take the Fourier transform of this equation now with this definition. So, I get this equation, the nonlinear Schrodinger equation, which is d u tilde by dz equal to j beta 2 by 2, and this will become minus omega square u tilde. So, as I said, the second derivative in time in the frequency domain, that will be multiplication by the frequency square. This equation can be solved very easily as a function of z. So, now if you know the pulse in the Fourier domain, the spectrum of the pulse at distance z equal to 0, then the u tilde at any location z can be written as u tilde 0 omega at z equal to 0 times the phase function, which is just coming because of this. So, e to the power minus j beta 2 omega square z upon 2. So, the solution in the Fourier domain, if you see for the nonlinear Schrodinger equation, when only the dispersion term is present, is this. What does that mean? If you look at this quantity here, you will see that this is the amplitude spectrum of the pulse, and that's what is the phase which you are going to get. So, initially whatever spectrum you had, which was this, after a distance z, the amplitude spectrum still remains unchanged. Only thing what happens is each frequency component undergoes a phase change, which is given by this. So, one thing first we note here is that in the presence of GBD, the amplitude spectrum of the pulse remains unchanged. Only a different frequency component, they undergo a phase change, and that phase change is proportional to the frequency square. So, the spectrum in the presence of GBD does not get modified. However, since the phase is going to change for the different frequency components, the time function will get modified. So, in the presence of dispersion, the spectrum of a pulse remains intact, only the phase spectrum changes, but as a result of this, the amplitude function of the pulse or the pulse shape gets modified. So, here we are seeing that you are having the phase of different frequency components that is proportional to omega square. It is also proportional to distance z. So, more the pulse travels on the optical fiber, more is going to be the phase change in the different frequency component. With this now, one can take the Fourier inverse of this quantity to find out what the pulse shape would be. So, one can get the time function, which is the pulse shape in time domain. So, u z t, that is equal to 1 upon 2 pi as we define the inverse Fourier transform, minus infinity to infinity u omega multiplied by e to the power j omega t, the Fourier inverse term, plus the phase term which is coming because of in the solution as we got here this term. So, minus j beta 2 upon 2 omega square z d omega. So, this expression now is a general expression. We have not taken any specific shape for the pulse. Only thing, we started with some pulse shape which was u z t. We took its Fourier transform to get the spectrum, and then we saw that the different frequency components undergo the phase change. So, this term if we add to the Fourier inverse, then we can get the pulse shape at any distance on the optical fiber. However, the analysis can be rather simple for a pulse shape which is Gaussian in nature. So, what we are going to see here is the evolution of a pulse which is Gaussian in nature, because there we can get a expression, right, which where the visualization can be much better. So, let us consider now that the pulse which we are launched inside the optical fiber is Gaussian. So, let us say we are launching a pulse at z equal to 0, which is e to the power minus t square divided by 2 t naught square, where t naught is the standard deviation of that Gaussian function. The half power width, if we define for this pulse, so this pulse is Gaussian in nature. So, sigma for this pulse is given by this t naught. So, the half power width, if I define for this pulse, so t full width half maximum, that is approximately 1.66 times this quantity t 0. Since we have to take the Fourier transform of the pulse, the Fourier transform of this, which is u tilde 0 omega, that is equal to root 2 pi t 0 e to the power minus t 0 square omega square upon 2. It is just the Fourier transform of this function. And as we know, the Fourier transform of a Gaussian function is another Gaussian function. Now, we have to substitute this into this equation and then take the inverse Fourier transform to see what the pulse shape would be as a function of distance. So, essentially this integral which we are seeing here, it is of this form, minus infinity to infinity minus a x square plus b x dx, and this is a standard integral identity for which we know the integral, that is pi divided by a exponential minus b square upon 4a. So, we can use this standard integral identity to solve this Fourier transform. So, once I get this pulse shape here, I substitute into this, identify what is the a and b, and then I can use the standard identity to find out what the Fourier transform of this would be. So, if I just substitute this, I get the Fourier transform as u z t, that is 1 upon 2 pi minus infinity to infinity root 2 pi t 0 e to the power minus omega 0 square omega square t 0 square upon 2. The phase function e to the power minus j beta 2 omega square z divided by 2, and the Fourier inverse term j omega t d omega. So, from here then we can identify what this a and b are. So, if I compare this expression with this expression here of the standard integral, we get a, which is t 0 square upon 2 plus j beta 2 upon 2 z, and b j times And then using now this standard integral identity, we can get the inverse Fourier transform of this. So, I get a u z t that is equal to 2 pi t 0 upon 2 pi square root of 2 pi divided by t 0 square plus j beta 2 z exponential minus j t square divided by 2 times t 0 square plus j beta 2 z. So, one thing one will note here is that this function is also a Gaussian function. So, I can separate out real imaginary part for this function. So, you will see that this thing can be written in terms of the phase function and the envelope function. So, u z t can be written as real part of this will become minus t square upon 2 t 1 square, where we will define t 1 plus the phase function some e to the power j some phi. And if we separate out real and imaginary part of this, you will notice that this quantity here t 1, which is a function of z, that is equal to the initial pulse width t naught 1 plus z by L d whole square power half. And as we know, the L d is defined as t naught square divided by mod of beta 2. So, now the L d, now physically we can see a meaning of L d, what the dispersion range really means. So, what this is telling you? This is telling you now that the pulse width originally which was t naught, now the pulse shape has still remained Gaussian, but the width of the pulse is changed from t naught to t 1 and which is given by this expression. So, if I take the distance z equal to L d, which is the dispersion length, this quantity will be equal to 1. So, this quantity will be equal to root 2. So, what that means is now physically the dispersion length is that length over which the pulse width increases by a factor of root 2. So, you will see at L equal to L d, the pulse width t 1 is root 2 times t 0. We can take the imaginary part of this and then we can get the phase function a phi, which is given by phi, which is equal to sine of beta 2 z by L d divided by 1 plus z by L d whole square t square divided by 2 t naught square minus 1 upon 2 tan inverse of z by L d. Now, note here that when we are looking at the phase component of this function here, there is one phase term which is going to come because of this and another phase term which is going to come because of this. So, the first term which you are seeing here, this quantity, that is coming because of the phase term here, and this one is coming because of the phase term of this quantity. So, that is the total phase you are going to see inside the pulse. So, first thing what we will note here is that the phi, the phase changes quadratically with time. The phase is related to this quantity which is t square. So, if the phase is changing with linearly with time, then the rate of change of the phase with time, that gives you frequency, that frequency remains constant. But since the phase is not a linear function of time, there is a frequency change as a function of time. So, what we are essentially now saying is that initially when the Gaussian pulse were launched, there is a carrier which has the same frequency for the entire duration of the Gaussian pulse. But now, since you are going to have a different phase change at different locations of the pulse, because the phase is a function of time and that is a nonlinear function of time, there is a frequency change which will going to take place, and this frequency change is going to be different at different locations inside the pulse. So, if I look at this Gaussian pulse, here I will see the phase change in the carrier at this location, which will be something, there is a certain frequency here. If I go here, the frequency would be different. If I go here, the frequency would be different, and so on. That means, initially the entire frequency was same inside the pulse, but now you see that the frequency is changing at different location inside the pulse because of this nonlinear phase function. So, since I have the expression here, we can get the change in frequency which is delta omega, that is equal to d phi by dt. So, I can differentiate this quantity here with t. So, you get change in frequency delta omega, that is equal to sine of beta 2 z by L d divided by 1 plus z by L d whole square t upon t naught square. That gives the change in frequency delta omega proportional to. That means, inside the pulse the frequency is going to linearly change from one end of the pulse to another end of the pulse. This phenomena of change in frequency is what is called the chirping phenomena. So, this gives what is called the frequency chirp. So, it is some kind of a frequency modulation which has taken place inside the pulse. So, initially when we consider a Gaussian function, the Gaussian function had a same frequency inside the pulse, but because of the dispersion there is going to be a frequency modulation inside the pulse. So, what has happened because of dispersion? That the envelope inside the pulse, if we really see, then whatever the constant carrier frequency was there inside the pulse, that is now frequency modulated, and this frequency modulation gives you linear change in frequency across the pulse. That is the effect of the group velocity dispersion. That is what we see from here. So, now since the frequency is changing linearly as a function of time, and now not only that, the change in frequency depend upon what is the sign of this beta 2. And as we know that inside the optical fiber, the fiber has a characteristic that it has an inflection point. So, if I plot the refractive index as a function of frequency for the optical fiber, then somewhere the beta 2 is positive, somewhere the beta 2 is negative. the region where beta 2 is positive is called the normal dispersion regime. When beta 2 is negative, that regime is what is called the anomalous dispersion. So, inside the optical fiber, we see beta 2 greater than 0, this we call as the normal dispersion. And this happens, if you look at the refractive index curve for optical fiber, this happens for wavelength less than 1300 nanometer. So, for lambda less than about 1300 nanometer. The beta 2 becomes less than 0 or it becomes negative. This happens for lambda greater than about 1300 nanometer, and this regime is what is called the anomalous dispersion. So, now if I take this change in frequency function and plot that as a function of time, I can see so this is time, this is the change in frequency delta omega. So, at z equal to 0, there is no change in frequency everywhere as a function of time, the frequency is same, so change in frequency is 0. So, this one gives you for z equal to 0. As the pulse starts moving, as the z increases, you have now the frequency change which is linear, and if I consider the sign of beta 2 positive, then the frequency increases as a function of t and it goes from negative to positive. So, if we have a situation which is like this, this is for some value of z 1 greater than 0. If I go to still further distance, it remains linear chirp, but the slope of this changed. So, this is for z 2 greater than z 1 and so on. Now, this happens if beta 2 is positive. That means, I see the frequency chirp which is positive like this for beta 2 greater than 0. So, normal dispersion, that is the way the frequency chirp is going to be. On the other hand, if I consider beta 2 less than 0, that is the anomalous dispersion regime, then the frequency chirp is negative, because now this quantity here is going to become negative. So, the frequency chirp is still linear, but now it will go like that. So, this is the, let us say, some z 1 greater than 0, this is z 2 greater than z 1 and so on. So, you see two different types of chirps inside the optical fiber pulse, depending upon what wavelength we are using. So, if we are below 1300 nanometer, where the dispersion is normal, we see the positive chirp of frequency. If I am at a wavelength greater than 1300 nanometer, then we see the negative chirp of frequencies. So, if I am operating at 1550 nanometer, this quantity would be the one. So, at 1550 nanometer, we see a dispersion which is the anomalous dispersion. So, we see here the anomalous dispersion. But note here, whether dispersion is positive or negative, you will see that the pulse width always increases, because the LD, which is defined as mod of beta 2. So, whether dispersion is positive or negative, you will see that this quantity is always increasing as a function of z. So, whether you are in the normal dispersion regime or you are in the anomalous dispersion regime, the envelope always broadens, and that is the phenomena, which is the dispersion phenomena, that when the pulse starts propagating on the optical fiber, there is always broadening of the pulse. That is what we have studied when we were studying the linear propagation in the optical fiber. But the chirping of the pulse inside the optical fiber or inside the pulse is going to be of opposite sense, depending upon whether you are in the normal regime or you are in the anomalous regime. So, now what is the meaning of this positive chirp then and negative chirp? So, what this means is that if I consider now a pulse which is like that, and this is the time, this is the center which is capital T equal to 0. So, this is the pulse edge which is the leading edge of the pulse, and this is the trailing edge of the pulse. So, now if now the change in frequency is positive, what that means is that here the frequency is little lower compared to the center, and here the frequency is little higher. That means the low frequencies get accumulated at the leading edge and the high frequency get accumulated at the trailing edge. But if I consider the anomalous dispersion regime, then the case will be exactly opposite, because now the frequency will be decreasing. So, here I will have, as a function of t, the frequency is decreased now. So, here I will have low frequencies and here I will have high frequencies. So, you see now that depending upon the situation, we may have a situation like this. You have the original pulse which is like this, there is inside this which is given as the carrier, and you see there is a same frequency everywhere. When the pulse starts moving on the optical fiber and there is a dispersion. So, when beta 2 is greater than 0, that means the normal dispersion, you see the low frequency got accumulated here and high frequency got accumulated here. When the dispersion is anomalous, that time the high frequency got accumulated here and low frequency got accumulated here. So, what has happened is that in this situation, the low frequencies have gone ahead, because this is the leading edge. In this situation, the low frequencies are left behind and the high frequencies are gone ahead. So, if I consider the situation like this, then you will see high frequencies move faster than the low frequency in the anomalous dispersion regime, and exactly opposite happens in the normal dispersion regime. But in both the cases, the spectrum remains same, only the phase of different frequencies are getting modified. So, here is the sort of pictorial representation of that, that there is a function of distance. If you start with a pulse, the pulse was like that, and doesn't, irrespective of whether you are having anomalous dispersion or normal dispersion, the pulse broadens, but the spectrum remains same, because the amplitude spectrum does not get modified, only the phase gets modified. So, here we are seeing the initially the pulse was like that, after a distance the pulse is broadened, right, it gets further broadened, it gets further broadened, and so on. So, initially if you start with a Gaussian pulse, you will see as the pulse travels, the shape of the pulse remains Gaussian, but its broadening continues as the pulse propagates on the optical fiber, and there is a frequency modulation, linear frequency modulation inside the optical pulse. So, let us to summarize, what is the effect of group velocity dispersion? The group velocity dispersion modifies the pulse shape in time domain. The amplitude spectrum of the pulse remains intact. What however modifies is the phase of different frequency components in the spectrum. So, the amplitude spectrum is same, but the phase spectrum changes, and as a result of that the shape of the pulse in time domain changes. And irrespective of whether you have the anomalous dispersion or you have the normal dispersion, the pulse always broadens, but with different frequency modulation inside the pulse.